In this video, we are going to talk about contour integrals. They're integrals of complex valued functions of a complex variable t. So what is different about this when we previously did integrals is now our variables are complex. And now I'm going to do this little aside, which you have maybe seen before, and certainly this will not be the last time, because it's important to understand that when you have real valued functions with real variables, and actually even when you have complex valued functions with real variables, when you integrate from a to b, that there's only one path from a to b because you're going from the real number a to the real number b. So you have to go through all the real numbers in between a and b, and you finally get to b. And the reason why I'm using real valued functions is because I can graph it this way. And again, the idea is that these real values for what you plug into f, the domain, can all fit on one axis. And so there's one path from a to b. Whereas here now, your domain is, if you're going from z1 to z2, so z1, your starting point for your integral, now needs an entire plane to represent z1. It needs an x and a y axis. And your z2, your ending point, analogous to b over here, also needs the entire plane, an x and a y coordinate. And so now the path from z1 to z2 can have all kinds of paths. So we can do the straight line from z1 to z2, but unlike the real numbers where the straight line is the only path, here I can have like this curved path, or I can have some totally random path. And the idea, again, is now our function then maps our z1, f of z1, and it maps our z2, f of z2, and it's these values, the function values, just like here we're integrating, we're kind of summing up all these values along this curve. Now for our complex values, we're summing up all the curves along the path. And so the idea is the path you choose is going to affect your integral. Coming back from our aside then our integral now is defined in terms of the values of f of z along a given contour. So like we were looking at over here, extending from a point z1 to z2 in the complex plane. It is a line integral like what you studied in vector calculus, and generally its value depends on the contour c as well as on its function. So we write that the integral along the curved path c, f of z dz. And if it turns out, because of properties of f, or then if this integral is independent of the path, we can write it as z1, z2, f of z dz. Cases where the integral is independent of the path over here will be studied later in this chapter. In general, though, the line integral would depend both on the contour as well as the function. And here we have a formula for this integral, the integral along the path c of f of z dz, and it's equal to a to b, and again a, b are the parameterization of our curve c, f composed of z of t is our parameterization, times z prime of t dt, and again z of t is our parameterization. So the three steps we need to compute this integral then is first to parameterize the curve z of t, noting the interval for z of t. So in other words, t goes from a to b. The next is to compute f composed of z of t. So we plug in our parameterization into the function f, and then we take the derivative of z of t. And then we plug this f composed of z and z prime of t into our equation. Associated with the contour c is the negative contour c, which consists of the same set of points but with the order reversed. So in other words, maybe instead of going counterclockwise, you go counterclockwise. So the new contour extends from point z2 to z1. And the contour negative c has parametric representation, z of negative t, where t goes from negative b to negative a. The other thing you can do with contours, you can break them up into pieces, especially like if you have a piecewise contour, like something that goes like this and then like this, you can break this up into C1, C2, and then your contour could be, you can do the contour for this half and then for this half. So the integral of C can be equal to the integral of C1 plus the integral of C2. And this is one of the examples we will be doing. Now we're ready to look at things in detail. So again, we're looking at integrals of complex valued functions of a complex variable z. So before, when we previously looked at integrals, we were doing complex valued functions of real variables, and we found that there weren't a lot of adjustments we needed to make compared to doing integrals we did first year calculus. But now that we have a complex variable, it's going to be different. We have to do something called a line integral, which you may recall from vector calculus. And the reason for that is that, well, when you have real value functions with real variables, the real variables, there's only one path from real variable A to real variable B, because the real variables can be represented, or the domain of your function can be represented by a single axis. So there's really only one path between any two real variables. Whereas a complex valued variable, a complex variable, is going to be represented in two dimensions. So it takes an entire plane to represent z1. So here we can say A is equal to z1, and B here is equal to z2. Well, z1 then, we need an x-coordinate and a y-coordinate because we need to express the real and the imaginary parts of z1. Similar for z2. So now that we have z1 and z2, and again, our function f then maps our function f of z1 to f of z2, then the values, basically there are multiple paths from z1 and z2. There's the straight path, much like there's the straight path between A and B, but as you can see, here I drew, there's also a curved path. And there could be all kinds of really strange paths that go from z1 to z2. And then here, my curved path maps, once we map f, maybe it maps to this other curved path here. And what we're integrating is we're adding up all these values f of z1, just like when we integrate here, we're adding up our heights, right? So here we're adding up all these values. So the curve we take is important because really, the values of f of z from here to here, it's a totally different path, and you'll have totally different values that you're summing up in your integral. One other comment I wanted to make is in first year calculus, when you integrated real valued functions with real variables, you could interpret this integral as the area under the curve. Here, there's no such kind of interpretation for you. The next thing we want to look at is this formula here, which tells us how to do this line integral. So it's the integral on the curve C, f of z dz. Looking at this formula that we have for the integral of c, f of z dz, you notice that first we have to compose f with z of t. And the idea here is much in the same way you're adding up the different values of f of x as x goes from a to b. You're summing up the values of f of z as z goes from z1 to z2. And so you don't really care about the values of f outside of this curve, which is why, and you only are concerned about the values of f on the curve, which is why you plug in the parameterization into f. Again, f, you're only concerned with the values of f on the curve. So you plug in your parameterization into f. This z prime comes from a chain rule somewhere, which we're not going to develop this formula. But you do have to remember to multiply it by z prime. And again, this z prime is your parameterization. One other comment I'm going to make, if you recall when we talked about parameterization, here I have t as our parameter, but often our curve might be parameterized by other functions like theta, or maybe it's parameterized by x or y, or here, this x or this y. We'll see some different examples. And when I use this formula, I wrote down 3 steps that you might want to follow, or you might not. You might just plug in directly into the formula. But the idea is the first step you want to do is to parameterize the curve, z of t, and you want to note the interval for t. So in other words, t goes from a to b. You need to know these a's and b's because they will become your limits of your integration. Then you're going to compute f composed of z and z prime of t, and then you're going to plug all the appropriate pieces into your formula. So we'll do some examples next. Here I've written the steps and I've written the formula. So the first problem is to find the value of the integral I along, the integral along c of z bar, or the complex conjugate of z dz, where z is equal to 2 e to the I theta. Theta goes between negative pi over 2 and pi over 2. So the first step is to parameterize the curve, z of t, noting the interval for t. So actually this is kind of easy because the curve has already been parameterized for you, and the variable that it's parameterized is not t, but theta. And here I've just made note of my step 1. Z of theta is equal to 2 e to the I theta. Theta goes between negative pi over 2 to pi over 2. My next step is to compute f composed of z and z prime of t. And this is function composition. That's what I mean by f composed of z. So my f of z, I identify that as z bar. So f composed of z of theta is equal to, so I want to plug in my parameterization of my curve, 2 e to the I theta into f. So that means I want the complex conjugate of 2 e to the I theta. And you might want to write this out. You might skip this step, but e to the I theta is just e, the real part 0 plus I theta. So then the complex conjugate, you just multiply, you just change this I to a negative I, the 0 stays. So you have 2 e to the minus I theta. And then to take the derivative of our path, the derivative of this, you just multiply by the constant, so I have 2i e to the I theta. And now I'm ready to plug everything in to my formula over here. So I have the integral from a to b, so the integral, and now I have the a to b over here, negative pi over 2 to pi over 2. I need my f composed of z, which I wrote, where is that? F composed of z is 2 e to the I minus I theta. And then my z prime is 2i e to the I theta d theta. And then I did the multiplication and the integration, and my final answer is 4 pi I. Oh, and just to, I don't know, to be that way, I also drew this curve for you. So this, as we know, e to the I theta, when theta goes from 0 to 2 pi, that would be the full circle of radius 2. So it's a partial circle of radius 2, where theta goes between negative pi over 2, so in the negative direction, in the clockwise direction, pi over 2 gets us to here, up to pi over 2. And that's it for this question. Here's the final answer. Our next problem is to integrate the function f of z is equal to y minus x minus I 3x squared over c2, where c2 is the line going from 0 to 1, 1, or 1 plus I. And we're going to compare this to integrating f of z over c1, where c1 is the line, it's actually 2 lines, so it's the line on the 0 axis up to I, and then it goes over on this straight line here to I plus 1. And just a quick note, when we integrate over c1, we're going to use this property that we saw on our overview slide. So if c is composed of 2 joined curves, then we can integrate c1 over c1 and then add it over the second curve, c2. In this case, the first curve is going to be the curve O to A, and the second curve is going to be A to B. Let's just do c2 first, this path here. So the first step is we need to parameterize the curve z of t, noting the interval for t. So here, the curve is y equals x, like it's just the y equals x line. So I can parameterize this as x and x. Again, this captures the idea that this y coordinate is equal to x, and that's also equal to x plus ix. I can express this as x plus ix, and x is going to go from 0 to 1. The second step is we need to compute f of z of t and z prime of t. So f of z of t is equal to f of x. So let me see, where is our f of z? So that means we need our y coordinate, which is equal to x, minus our x coordinate, which is equal to x, minus 3x squared. So that's minus 3, and then plugging x, which is just x, squared here. So what I get is minus 3x squared. I made some indications now. When I plugged in xx into here, this is my x coordinate. So this corresponds to where I plug in for the green x's. This x is actually my y coordinate in my coordinate pair. So that's why I plugged in x for this y. So this y underlined in blue corresponds to this x underlined in blue. So kind of looking at that again, this comes from the y coordinate of this xy coordinate pair. This x here came from x, and this x came from my x coordinate in my xy coordinate pair. It just kind of looks funny since this is in terms of x's and y's and this is in terms of x's, but this y here refers to the imaginary coordinate of my z, and these x's refer to the real coordinate of my z. Now I can take my derivative. So my derivative, where is my z? Here it is. Z is equal to x plus I of x. When I take the derivative, this is going to be 1 plus I times 1. Now we're at our last step, which is to plug into our formula. So we're going to plug into the interval between a and b, and a and b is given to us by our parameterization, 0 and 1. And then we need our f of z of t, f composed of z of t, which is minus 3x squared. And then we need our z prime of t, which we calculated as 1 plus I. So after that, the rest is algebra and integration. So I'll leave that for you to verify. My final answer is 1 minus I. So now that we've calculated the integral of f of z over this curve, we're going to compare that to integrating f of z over this curve C1, which goes from O to A and then A to B. And I'm going to leave these calculations here for you for comparison, and I'm going to do the C1 curve on this side of the page. It gets a little cluttered, but I think it's worth seeing the difference. The first step, again, is to parameterize the curve z of t, noting the interval for t. So 0 to a, in this case, our x-coordinate stays at 0 while our y-coordinate varies. So our x-coordinate stays at 0, our y-coordinate will vary between 0 and 1. So that's our parameterization for OA. Now for A to B, at this point our y-coordinate stays at 1, while our x-coordinate goes from 0 to 1. So that's the parameterization we're going to have. Y-coordinate is 1, x goes from 0 to 1. The next step is to compute f composed of z and z prime of t. We have two paths. So f composed of z of t for OA, our first path, now is f of, in this case we're going to plug in 0y. Plugging in y, and then we have our minus 0, minus I, 3, and then our 0 squared gives us 0. So we just get y. For our path AB, we're going to have f of zt, and again, our z of t is equal to x1. So we're going to have 1 plugged in for our y, our minus x, and then our minus 3x squared. Next, I'm going to do the derivatives. So our derivative of z prime of t, so derivative of 0y is just 0, 1, which is equal to I. Remember, this is the coordinate for z, which is 0 plus 1 times I. Then the derivative for AB, that's where's z here, is going to be 1 and then 0 because there's no x-coordinate. I is just a constant. So 1, 0, which is equal to 1. Now what is left is to plug into the interval. So for our first curve, which goes from 0 to a, that's, let's see, 0 to a, our limits of integration are 0 to 1, and then we have our y is our f composed of z, and then we have our derivative, which is I, dy, plus, then for AB, now the limits of integration are also 0 to 1, and we have our, where is our f composed of that? We have 1 minus x minus I 3x squared times our derivative, which is equal to 1. And the rest is just integration and algebra, and I get negative 1/2 I plus 1/2. And one of the main points of this example is to show that the two integrals are not equal. Here we get 1 minus I, and here we get minus 1/2 I plus 1/2. And they're not equal because this integral is dependent on the path. Here we're going to let C denote any arbitrary smooth arc, z equals zt, t goes between a and b, from a fixed point z1 to a fixed point z2. So I just drew a random path from z equals z of a, z2 is equal to z of b. To evaluate this integral, we're going to note, when we take this integral, we're going to have a to b z of t. This is our, plugging in our path, z prime of t, that the derivative of z of t over 2 squared is equal to z of t, z prime of t. So that's exactly what we have here. So then when we take the integral of c dz, that's equal to z of t over 2 squared evaluated at a and b. You can plug in your a and b, and then you get z2 squared minus z1 squared over 2, which means that our integral is equal to z2 squared minus z1 squared over 2. There was nothing we had to include about the path. In other words, this function z, this integral depends only on the endpoints, and it is independent of the path, unlike our previous example. Furthermore, if c is a closed contour, we'll see that the integral is equal to 0. And so this, when the value of an integral around a closed contour has value of 0, we're going to investigate that later on in this chapter. But mostly, this example is to give you a contrast to our previous example where the curve, different curves will give you different values for the integral. This function here will not. It's totally independent of the curve. And now we're ready to review what we've discussed. First, we are talking about contour integrals, and again, the important part is these are complex valued functions for complex variables. And when we have that situation, then we need to determine what contour, C, that we're integrating along. And then basically we're computing a line integral, and the value of this integral, the value of the integral on the contour C of f of z dz depends both on the contour as well as the function. We have, if f is piecewise continuous on the interval on C, then we have this formula for the integral of C, the integral along C of f of z dz. That's equal to the integral from a to b, f composed of z, our path of t, z prime of t dt. And I had these 3 steps in order to do these path integrals. The first one is to parameterize the curve z of t, noting the interval for t. Then to compute f composed of z of t and z prime of t. And then we just plug into our formula. We didn't do an example of this, but you can parameterize a curve so that it goes in the opposite direction. So if your curve, for example, normally goes from z1 to z2 in this tiny picture, you can parameterize it to go from z2 to z1 by using this parameterization here. But normally what I do is I just compute the forward curve, and if I want to know what the integral is of the backwards curve, it turns out that the backwards curve is just the negative of the forwards curve, which is why I don't really remember this parameterization. But that's something I did not show an example of, but this can come in handy. Then the other thing that we did use is if we want to break our curve up into two curves that join together, we can then integrate on the first curve and then just add it to the integral of the second curve. And then we did this example here where we were finding the integral of along C, where C is the right side of z equals 2 e to the I pi, which is this curve here, the integral of z bar dz. So the first step is we parameterized our curve, noting the interval for t. So here z is actually a function of theta, so it's not z of t but z of theta, but it was given to us. So z is equal to 2 e to the I theta. Well, the right side, so we had to know that that would mean theta goes from negative pi over 2 to pi over 2. Next, we computed f composed of z, so we simply plug in our z, our parameterization, into f, which is z bar. So it's 2 e to the I pi bar, which is equal to 2 e to the minus I theta. And then we calculate z prime. So z prime, where is z? We just take the I, the constant, down, so we have 2i e to the I theta, and now we can plug into our formula. We go from a to b, and a to b is given in our parameterization, negative pi over 2 to pi over 2, f of z of t, which is 2i e to the I theta, times our derivative. Oops, I'm sorry. Our f of z of theta is 2 e to the minus I theta, which is here, and then our derivative, which is 2i e to the I theta. And the rest is just integration and calculation. Our final answer was 4 pi I. Next, I have two contour integrals for you to try. So the first one, f of z is equal to z plus 2 over z, and c is the semicircle of radius 2 in the upper xy plane. So if here is my xy plane, I want this part of the semicircle of radius 2 centered at 0, 0 in the upper xy plane. The second problem, f of z is equal to 1 when y is less than 0 and 4y when y is greater than 0, and c is the arc from z equals minus 1 minus I to z equals 1 plus I along the curve y equals x cubed. I am going to suggest that you pause the video, give these two problems a try, and when you come back, I will have solutions for you. Here is the first solution as well as the drawing of my semicircle. The second problem I had done two ways. The first one I had parameterized. As you know, you can actually have multiple different parameterizations of the same curve. So the first time I parameterized my f of z as x cubed, x going between negative 1 and 1. And then later I realized just the way this function was written, it was probably easier to parameterize my function as y to the 1/3 y, where y goes between negative 1 and 1. So here it is, and I can claim I did this for your benefit. I've done this problem two different ways, two different parameterizations. And that's it for this video. Thank you for watching.